right. How many students are here?
Yep. How are you?
Hey, good afternoon.
Good afternoon.
All right, students, let me test my camera. Or are you able to see my screen now?
Yeah, I can see it.
I just set up the Dropbox for today. I will be collecting the report. And a lot of you did very well in the spinach experiment. I finished grading it. And so I plan to do this, like for every two experiments, I will post your grade book. I'll create a grade book on Beachboard. I will not integrate my gradebook with the Beachboard gradebook, okay? It will be just from my own sections. I have section 2 and section 4. I'll post the gradebook at the same time without showing your name, okay? Just your ID. And I do that, you know, every 2 or 3 experiments, okay, during the semester. Okay? So let me wait. I mean, I think I have a minute to go. So remind me, I need to create a Dropbox folder for this Diels Alder report, okay? So how's everybody here? Not bad? Pretty good? Exciting?
Not bad.
Yeah, think positive, okay?
Mm-hmm.
Life is difficult for everyone. But if you live through it, you're just tougher. You're a lot more capable than you think. Why not? Why don't you see your own capability of making a breakthrough each time you encounter problems, right? I like it. I like it. I mean, I never knew I'm able to do this much. Oh, no. But after you finish, if you survive, you really become a much stronger person, okay? All right, students. Now someone gave me a comment. Eating lunch finally. I know. Yeah, you can eat your lunch, okay? No problem, okay? Today I plan to review a little bit on your Diels Alder reaction. I heard you had it last semester, maybe, okay? That you probably forgot. And I want to, I think I gave you the feeling, you know, the Diels Alder reaction is amazing. It has a tremendous application in industry, okay? We can build new carbon-carbon bond. That is always desirable, okay? You know, especially in the pharmaceutical world, you do want new molecules, okay? All right. And so let me pull the document camera. All right. All right, are you ready? No, guys, help me. Okay. You know, when you help me, you're able to collect some points, right? Actually, a lot of you, when I check the pre-lab quiz, I think you can do better than what I see here. The class average is actually less than 60%. Yeah, a little bit less than 60%. And I think you can do better. That's why I want to give you bonus point opportunity, okay? The report part, most people do very well, okay? I mean, class average, I think in the range of A, not bad, okay? But if it's too good, I wonder whether you are not making effort, just take someone else's answer. I hope this is not the case, okay? All right, so let me do this, okay? Let me start writing the Diels Alder reaction, more example. Okay, more and more example. The more example you see, the better. Are you able to see my screen? Hello?
Yes.
You see like the corner of some paper.
paper.
Yeah, we see the corner.
Are you able to see the color of the pen?
Yeah.
Yes.
Yeah.
Yes.
Love it. Okay. All right. So in order to run a Diels Alder reaction, you need to have a dienophile, right? And a double bond somewhere. Am I right? Hello?
Yes.
Yes.
Yeah.
Thank you. So what is a dienophile? We had this 2,3-dimethyl 2,3-dimethyl, and then is 1,3-butadiene, right? This is one of our reactant, am I right? And you use malignant hydride. So which one is dienophile? Dienophile? Dienophile. What does it mean? It likes diene, right? So what likes diene? The multiple bond, right? Hello?
Yes.
Can you run the Diels Alder with a single bond here? No way, no way, okay? All right, and I told you this is actually favored because the 6-member ring is a comfortable arrangement of the carbon-carbon, okay? So your end product, okay, let me minimize this, okay? Your end product from day 1, this is from last week. Am I missing something? This is what I call the cyclo-addition product, right? Or cyclo-addition adduct. Cyclo-addition. You make a ring, 6-member ring. Am I missing a double bond somewhere? Is this the right place?
No.
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 Here?
No.
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 Yes.
Yes.
Yes, thank you. All right. So what's big deal? Well, you made a new bond right here. That's what's big deal, okay? And it's covalent bond. Covalent bond is strong, okay? All right. And today we're gonna do hydrolysis, am I right? And we're gonna be using water to do the attack, okay? And of course, some catalyst here. What was the catalyst here today? Any idea?
HCl.
HCl, and what is doing the active catalysis? It's coming from the proton, am I right? Okay. And what else are you what else do you have to add in order to make the reaction go? There's something else. What is it?
Do you have water?
You add water. Water is right here.
Oh.
Besides water, what else do you have to add?
Is it acetone?
Acetone. Thank you. Acetone must be added as a solvent, okay? You're gonna run this reaction in acetone. Why do we have to use acetone? Because I have to dissolve everything together, right? Okay, is acetone a good solvent? Yes. Okay, you want to put your product from day 1, you want to put HCl, okay? You want to put water. Are they gonna like each other? In terms of solubility, are they gonna like each other? The answer is not really, because I told you last time, this molecule, you precipitate it in water, remember? You make the white powder when you pour the reaction mixture into ice water, I remember, hello? You don't remember anything, right? All right, show me page 100, your lab manual. Grab your note, grab your lab manual, okay? I'm grabbing it too.
Page 100 is empty.
Is it page 100?
I think the experiment starts on
empty.
page 98.
Okay, I have a different version of the book, that's why. So what is the page number then? Page 98, hello. Okay, page 98. I was close. All right, now ladies and gentlemen, help me read this. You add butadiene to the flask at the last, and after you introduce the maleic anhydride, you pulverize it, and then you mix them together using PEG as a solvent. Do you remember that? Hello, all the goodies. Yeah. Okay. Then when you work up, what do? You pour the reaction mixture into a beaker containing water to precipitate cycloaddition product. Water to precipitate cycloaddition product. Okay, what does it mean? That means the product can precipitate in water, right? Hello?
Yes.
Yes.
Product can precipitate in water. Product can precipitate in water. If it precipitate in water, does it dissolve in water?
No.
No. Okay, why not dissolving water? Why not?
It's more nonpolar.
Yes, it's more nonpolar, and we said that last time, right? So today, in order to run the reaction, you have to add, well, you add water actually water in this case is a reactant. But what solvent do you want to add today? What solvent do you want to add today? Acetone right here, am I right?
Yeah.
Acetone is doing the job. Okay, so what is the structure of acetone? What is the structure of acetone? Acetone looks like this, right? Am I right? Is this acetone to you?
Yeah.
Yeah. Are they similar in the polarity?
Yes.
Like, dissolve like? Do you see that? So is this going to dissolve in this? Yes. Okay. It looks similar, right? Okay. Then you can add water to do the hydrolysis. And today you want to break this molecule apart, okay? But this 6-member ring does not change. You are creating COOH. COOH. Have you learned this before? Hello? Anhydride decompose to create 2 COOH group, okay? So you will see, okay, the bond will break in between, okay? Might as well write it this way, okay? Okay, the oxygen here will take the hydrogen. The carbonyl group will take OH. Does it make sense to you? Hello? And that's called hydrolysis.
Yes.
That's called hydrolysis. You may say, Ms. Jean, is this ugly molecule with so many carboxylic group? Does it have any use at all? Oh my goodness. Look at this. You created 2 functional group. And so you can actually increase the molecule size by reacting the COH with something else. Are you with me? So there is a great application of Diels Alder. Increase the size, okay? Diels Alder first, and then you can make use of the COH and go further. Expand the molecule. Understand? You can create the ideal drug we're talking about. Okay, so far so good? Like it?
Yeah.
You like it? Okay. You may want to see the mechanism. Okay. I can tell you right here. What do you call this group? What do you call this group? There's a special name for it.
Carbonyl.
Huh?
Carbonyl group.
There is a special name for a CO double bond. What do you call this group?
Ketone.
It's not ketone. There is a special name for it. You can't say ketone because there is oxygen here, and it's not ketone anymore. Okay.
Is it not a carbonyl group? Oh.
Have you heard of this term? Carbonyl group? Not yet. That's fine. No problem. I just want to share with you. Okay. You have a 5-member ring. Okay, this is from last time, and I want to keep going. Can you help me and tell me in this functional group, carbonyl group, and oxygen, and we call this anhydride total. We call this whole thing anhydride. Okay, this whole thing is called anhydride. Yeah, it's anhydride again. Just like maleic anhydride, you have that 6-member ring, a 5-member ring. 1, 2, 3, 4, 5. Okay. All right, help me, students. Is this bond 100% covalent? Is this bond 100% covalent? When I say 100% covalent, is this 100% covalent? Is this 100% covalent? That means I'm asking you, is this polar? Hey, what's going on with this class now? Is this 100% covalent? Yes or no? Can you just answer yes or no?
No.
No?
Yeah, no.
Is this 100% covalent?
No.
Oh,
I think it is.
I think you're overthinking now. Is this a covalent bond?
Yes.
Yes.
Okay, that's what I mean, okay? Is this covalent bond? Yes. Is this covalent bond? Is this 100%, I mean, is the electron density equal everywhere in this bond?
Does the dipole moment mean like there would be ionic character to it?
Some polarity, am I right? Have you seen this symbol of dipole moment? Hello?
Yes.
Yeah.
Okay, can I draw it this way here? I can't, right? I cannot do it here either. No. So this is called covalent bond. Let me not over challenge you. Is this covalent bond? The answer is yes. This is a covalent bond, yes. This is not 100% covalent. This is a polar bond, okay? Are you all with me? Okay, all right. So is this bond 100% covalent? The answer is not, right? The answer is not. So if I ask you the polarity, which side is more electron rich, oxygen or carbon?
Oxygen.
Oxygen is more electron rich, right? So can I write it this way? Have you seen this? Have you seen such a symbol?
Yes.
Partially positive and partially negative? Yeah, okay. I'm glad you've seen it before, okay? And so what does it mean to this hydrolysis reaction then? Okay, now you are adding you're adding hydrochloric acid, you're adding water at the same time, okay? And most likely this is what needs to happen, okay? Okay, this carbon, oxygen, okay, right here, attract. Are they going to attract each other? Because this is partially positive, negative. Does it make sense?
Yes.
They
Yes.
attract each other, okay? and there is a partially positive right here, okay? And so go ahead. Make this. Hey, I don't know whether your professor helped you write the mechanism, okay? Have you seen this before? Have you seen this before? Or it is possible to just use the lone pair, okay? Lone pair, lone pair, lone pair. Share the electron pair with hydrogen plus, and you can do it this way. Then you can move the electron. Have you seen this before? Hello?
Yeah.
Yes.
All right, you've seen something similar. Okay, then what happened? Then you create OH. Okay, now this oxygen is happy. And something like this, right? Right? And at the same time, this carbon is gonna be plus charge because you're removing that electron pair. So it becomes plus charge. And so this is not happy. So what must happen? What must happen?
We're gonna stabilize it.
To stabilize it. So how do we do it? You can actually break the bond, okay? Break the bond. It has to dissociate, okay? Because this is not happy. So what happened is, right after this, okay, students, are you able to follow me? Right after this, okay, go ahead, OH, okay, then this carbon is right here, no problem, okay, CO, O, O, okay, with oxygen, like this, right?
Yeah.
Do you know what I'm doing? I'm showing you hydrolysis, okay? Okay, and this plus charge right here, okay, there's two ways. If you just stop right here, Miss Jean, I'm confused. You don't have to move the electron, okay? Just do it this way. I have a plus charge, okay? And, okay, I have this oxygen with a lone pair, no problem. Then this carbon will be attracting the water right away, okay? Are you with me? Hello?
Yeah.
Okay, and then what happened? Okay, COH, okay, then oxygen, H, then this oxygen would not be happy. It's a plus charge. When I say it's not happy, it's because, okay, if there is a charge without a counter ion to balance the charge, then it won't be happy. I mean, it's too hot. It's actually a high energy state, okay? So this will cause the bond to break, okay? And then you will see, all right, what is the best way to break it, okay? How about this go away, and then I can create COO minus charge here, okay? And then at the same time, COH, okay, O, hydrogen. Are you able to follow me?
Yeah.
Okay, and this is a plus charge. It's not happy, so must sacrifice one covalent bond, then release the hydrogen plus, then this hydrogen will be taken by the carboxylate, okay? So what I'm saying is the COOH, okay, will be created today through this we call the hydrolysis mechanism, okay? And you can do it either in the acid or base. It doesn't matter, okay? The main thing is this is a bond right here. This is a bond, okay, that will be easily attacked by either acid or base. Strong acid, strong base definitely will kill it. Okay? Strong acid or strong base, either one. But today we choose to use the HCl. Okay, students, are you able to see how it goes? The water is doing the actual attack, and this is a catalyst, okay? And if you have problem understanding it, no, you can Google it, okay? Whatever I said, it's actually on the Google, all right? And I mean, people don't want to buy textbooks, so I can only say, hey, go ahead and check the Google, all right? All right, so before I show you any more video, okay? Today we're creating this, okay? Okay, it's gonna see a lot of potential creating more molecules if you continue to react the carboxylic acid, okay? And before I play the video, I want to review some of the questions I usually help students understand Diels Alder, okay? So if I say, this is my diene, okay? And I have dienophile like this. Okay, when you form Diels Alder reaction product, cycloaddition product, you're gonna be getting this, okay, just like today. And so what I want to say is, if you have a cis starting point on the dienophile, cis dienophile, then you will get cis cycloaddition product. Are you with me? Hello?
Yeah.
Okay, so cis will give you cis. Okay? If I give you this, what do you call this? A trans, right?
Yeah.
So tell me, what is your prediction for two axes? They're supposed to be in the opposite side of each other, am I right?
Yes.
Okay. And then, so what do you say? Is this the right way to draw it? The answer is yes. Okay, so cis produce cis, trans produce trans. You get it?
Yeah.
Okay. All right, so double bond is a very good dienophile. If I give you, another exercise. If I give you diene, can I give you this? A triple bond. Is this a dienophile? Is this a good dienophile?
I don't think so.
You don't
No.
think so? Is 6-member ring a comfortable arrangement here? What do you think? If I put them together? Can I make a 6-member ring?
Yeah, you could make a 6-member.
Okay, so the answer is this is also a dienophile. Okay? The same way. You hear me? So how do I make the end product? This is gone. Right? Hello?
Yes.
Am I missing something?
A double bond on the opposite
Well,
side.
yeah.
You need another double bond here. You're right. Okay? And then you have you will have your, okay? Good? How do you like it? Make sense?
Yeah.
Okay. Let me ask you this. If I have the double bond rearranged like this, and I want to make Diels Alder reaction. Is that possible?
Yeah.
Okay, imagine your double bond comes here. Okay. Can I make a 6-member ring? I mean, there's no atom here, understand? There's no 6-member ring arrangement. Do you hear me? It is only 1, 2, 3, 4, 5. Are you with me? Hello?
I
Yeah.
see. Yeah.
Okay, so in this case, what is NR?
No reaction.
No reaction. Do you get it? Okay.
Yeah.
You may not believe it. This is all in the book. See that? I'm just helping you to review. Hello, one more time. If you put your diene like this, there's no reaction because you're missing 1 carbon. And I told you that 6-member ring is crucial. You hear me?
Yeah. So just to clarify, whenever we're trying to do Diels Alder and we have our diene, we want to make sure our diene kind of like is in that cup formation.
You need to make sure they have a 6-member ring potential transition state. Okay?
Yeah.
If you cannot do that, then there's no Diels Alder. There will be something else. Okay? Are you with me? Are you with me?
Yes.
You cannot make 6-member ring out of this. Okay? That's why. Okay? All right. I want to keep going. Okay? Now, if I ask you, now this is a little bit just, to see if you understand Diels Alder, okay? You have the knowledge, but, I really want to push you to the max, okay? And I put a double bond here. Can I make Diels Alder reaction?
No.
I don't think so.
Amanda and Simon, are you able to rotate the bond?
No. Wait. It's a single bond, so yes.
You're right.
Yeah. Okay.
Yes, do you see that? You see how we want to trick you? Okay, it means the same, am I right? This is the same as that. Same. You're able to make 6-member ring. Do you hear me? Okay.
Yeah. Yeah.
Yeah, Diels Alder. Okay, just pay attention to the 6-member ring. All right. Now here is something a little bit for you to imagine then. Okay, I'll give you something else. Can I make Diels Alder?
Yes.
The answer is yes. Very good. Amanda, can you help me? Can you help me draw? Is this a 6-member ring?
Yes.
The same of
And then the carbonyl in the same position.
exactly. Okay. Let me tell you, such molecules so important in industry, okay? Oh, they will give you a whole bunch of reaction that also I want to share with you, because this is the reaction in the industry that we run all the time, and I don't want to scare you. This is actually quite possible, okay? So if I give you a diene the other way, if I give you diene like this, so what is, how many members of carbon are here? How many?
5.
5.
5. Okay. And I put a dienophile. Okay. So is this a good dienophile still? Yes, it is. Okay, and go ahead. The 6-member ring can be formed this way. All right, so what is the end product? Ooh, weird, huh?
Yeah.
Okay. Am I missing something? The double bond.
Double
bonds.
bond.
Okay. You may say, Ms. Jean, is this real? You guys run this reaction in industry? The answer is yes. Believe me, this group right here, tell me, is this water loving or water hating? Is this hydrophilic or hydrophobic?
Hydrophobic.
Hydrophobic? Hydrophobic, right? Hydrophobic, right?
Yeah.
Yes.
It's gonna be
Does not
polar.
have any polarity,
No,
right?
polar.
It's not polar. So Miss Jean, what is the application? We put a lot of these groups in the coating to protect from moisture attack. Okay? So when, especially for like, the coating you use for like marine application. Yeah, the ship. Yeah, the battleship in water. Okay? You cannot expose the metal to the salt water. You need to put coating. And what is the coating? It contains, we call it dicyclopentadiene kind of structure. Yes, super important, okay? So you may say, Ms. Jean, everything we do is nonsense. I can tell you, everything you do has a big application in industry. Do you hear me? Hello? Okay, how do you like it? I hope you like chemistry for some degree, okay, to some degree. It is actually quite unique, okay? Only through the Diels Alder you're able to do this, okay? Yeah, okay, all right, so are you guys ready? I can play some video now, hello?
Yes.
Everybody ready? Hey, what's going on?
Yeah.
It seems to me no one's awake. Are you all taking a nap? I hope not.
I'm just to talk.
I hope you're ready to enjoy some video, okay? The demonstration from our outstanding TA. I really miss him. He's now on the way to Switzerland, getting his PhD degree from some very well-known research institute and university. Hold on. I miss him a lot. His name is Philip Lee. Okay. I have to open from my personal account more. Sorry. Okay, draft. Crazy, right? I need to create a lot of my, a lot of YouTube video I actually create for educational purpose. All right, this is it. Okay, ready to go? Diels Alder. Okay, we finished at 8:30 last time. Did you write down the number? Hello?
Which number?
Which number?
All the grams.
We wrote down the cycloaddition product grams.
Yes. Did you write down the molecular hydride grams? You need.
Yes.
Yes.
Yes. Okay. So I'm just refreshing your memory. Okay. This is what we did. And at the end, okay, RTA, collect the cycloaddition product. And this is for you to.
We don't see a video. I don't know if you're showing the video.
My goodness. Oh, thank you. Thank you for letting me know. Do you see it now?
Yes.
Do you see a scale?
Yeah, we see it.
All right. So starting from this point, you are setting up the reaction flask with stir bar and water bath. Okay. Okay. Whatever you missed, let me replay it. Weigh out cycloaddition product. Okay, this is our starting point. Yeah, transfer the powder. Okay. Oh, by the way, hey, the TA was so nice helping me saying this is a powder funnel. What do you see in difference comparing the normal funnel you play with or you use during your Gen Chem training time? Is this different than usual?
Not that I can see.
Not that you can see. Okay, let me see.
Unless maybe that it goes over the tube or bottle. That's it.
Okay, I want to show you. It's actually right. Stop right there. Okay, one more time. One more time. Pay attention to the size and the diameter of the stem. Is it a big one or is it a fat one or a skinny one?
Skinnier.
Are you kidding me? You call this skinny? This is really large, okay? One more time. We want to show you what kind of a funnel you should use. Is this a big diameter right here?
Yes.
Yes. Okay, if you want to charge powder, you want a wide stem. If it is a skinny and very narrow stem, are you able to transfer the powder? Of course not, right? You would choke. You would choke the funnel tip right here, okay? See, it was easy to pour through it. All right. Once again, what is the purpose of acetone?
Solvent.
It's a solvent. And I cannot use water alone. Why is that? Why is that? Why is that? Why is that? Whenever you want to dissolve something, there is a big rule.
You gotta have like dissolve like and water.
Yes, acetone has a similar, carbonyl group, the CO double bond. That's why. Okay. Dissolve. Hey, by the way, tell me, students, are you able to make a reaction go without dissolving it? The answer is no. Okay. You can never run a effectively run a chemical reaction, you can never run a chemical reaction effectively unless you dissolve all the ingredients into the solution. Do you hear me? Okay, you cannot place two pieces of rock together, you know, solid and solid. You put them together and expect there is a chemical reaction. It doesn't go that way, okay? You want to dissolve them together. Do you hear me? Okay?
Yeah.
And for this reason, a lot of times, you know, the scientists are just so curious, when I change the solvent, does it change the yield? The answer is yes, okay? Oftentimes it does affect the yield, okay? And in this case, we're using acetone and water. Okay, acetone. Hey, by the way, is this the acetone from the reagent bottle, or this is the acetone from the wash station? Are you able to use the squeeze bottle from the station, the wash station? The answer is no, okay? That kind of acetone is just too dirty and low grade. You have to use the reagent grade, okay? From this kind of brown bottle, okay? All right, dissolve, okay, dissolve. You know, see, he's trying to dissolve it with acetone first, okay? And then add HCl, 2-3 drops. Yeah. Do you need a lot? You don't. Okay, it's a catalyst. Okay, and you stopper it. Hey, by the way, do you want to seal it? Do you want to completely seal and this is supposed to be airtight? Is it good or not?
Yeah, because you don't want it evaporating.
Now, Simon, let me ask you
Not
this.
like completely sealed up, because then that messes with the experiment. But you want it like closed system, sort of, almost.
Yes, you want to loosely attach the top so that you don't lose your solvent. However, you don't want it airtight, okay? If it's airtight, if you heat it and the vapor pressure builds up, what does it do to the glass?
It'll shatter.
Yes, it will shatter the glass. All right, students, are you here? Do you listen to me? Hello? This is all
Yes.
common sense, okay? Because let me tell you, some students so aggressive, okay, trying to seal this. Oh my goodness, they really apply a lot of pressure. And guess what? During the reaction, they just pop. Hey, when it pop, without hurting your eyes, it doesn't bother me. However, a lot of times they pop and become bullets, shooting at students' eyes. Is this good news? It's really terrible news, right? Okay, so be careful. When you heat up something, you want to make sure it is only loosely attached on the bottom, so on the top, so you can control the evaporation to some degree, but you don't want to seal and airtight the top, okay? Slowly heat up to this temperature. Okay? Do you see he's stirring all the time? Stir. What is the purpose of stirring it? Hello? Why do you have to stir? Hey.
You want to facilitate the what's called like equal spreading of it throughout the solution.
Spreading? Is there a better word than spreading?
There is. I'm just blanking out right now.
You have a better word for it, right, Simon? What is a better word besides spreading it? I want to spread the powder. But remember, I said if you put two pieces of rock together, are they going to react? No. You want the solid to dissolve. Am I right? Okay, this is the key word. You have to make sure it dissolve, okay? So 5 minutes, okay? Ooh, and you see immiscible oil beginning to form. Okay, now students, I want you to flip to this page number. Let me see. Is this page number 99? Can we look at page 99? And there's a note.
Is page 99 the notes and discussion portion, or is it the other page?
There is a note, note 8.8. The dicarboxylic acid derivatives is very insoluble and has a great tendency to recrystallize, okay? And besides that, I think there is something about the oil they were talking about.
Where it says it's like less likely to crystallize if you use acetone as a solvent instead of dichloromethane.
If you have okay, if it's very insoluble and a great tendency to crystallize. If you have trouble getting a good sample, try acetone. Okay, we're not doing the IR, so I'm not going to worry about this. Okay, the reaction product seems to have a less tendency to crystallize from acetone because don't forget, we have a carbonyl group, the CO double bond on the product. And the acetone is quite powerful. It's quite a good solvent to dissolve the compound. And you're not getting a good yield, okay? That's what it's saying. And the other problem is you will see oil begin to form. It's actually coming from the melting of the cycloaddition product, okay? Now, students, I want you to take a look at the melting point of the product from day one. What is it? The melting point of the product from day one. What is it? Are you able to find it?
The literature value?
78.
Literature value, yes. What is it?
Like Nathan was saying, it's 78 degrees to 79 degrees Celsius.
Exactly. So when you put in the water bath like this, you actually see the product melt. And when it melts, it looks oily. Understand? Okay, so this is what's going on here. Students, as I said, I don't have to tell you this much details if I don't care about teaching, okay? I just want to help you build the habit of observing some changes with your own eyes, okay? And if you want to be a good doctor in the future, when anything changes in the patient's, you know, the symptoms is changed, okay? The breathing rate has changed, okay? The activity of the patient change. You better know about it, okay? It's just like when you babysit a reaction, you better pay attention to the change of the reaction, okay? Hey, see? Do you see all the white powder disappear? Do you see all the white powder disappear? Okay, and then guess what? It's because dissolved. And then, slowly you see, you see this solid derivatives from the oils dissolved, okay? And reaction mixture becomes cloudy again. Tell me what happened when it's cloudy. What does it mean? When it's cloudy, does it mean something is precipitating now?
Yeah, something's precipitating.
Something is precipitating. So what is that? What is precipitating now? It is the final product of product 2. Understand? It is the COOH being formed, okay? And it does not precipitate until you cool down, okay? You want to cool it down. And the TA actually prepared the eyes to cool it down, okay? We'll see. Yeah, some cloudiness already there, but when he cooled it down, hey, when you cool down, is the solubility decrease or increase? Hello?
It's
Student?
harder for things to be soluble.
When you add ice, you cool down the temperature, the solubility of anything should decrease. Am I right?
Yes.
The mobility of the molecules actually decrease, okay? And so they aggregate and pack together and form crystal, okay? All right, you'll see suction filter. Oh, look at this, how much solid he actually collected from cooling down. Okay, this is the product too, okay? You guys see how it goes now? Until dry. Yeah. Okay, and he will show you. Yes. Okay, what are you looking at again? What is it? Hey, I want students other than Simon and Amanda answer my question. Oh, I think Nathan, is Nathan? Yeah, Nathan do sometimes answer my question as well. How about the rest of you? Hello? Are you still awake? Is Sabrina here?
Yes.
Okay. Esparza, are you here?
Yes.
Amanda, you're here. How about Gonzalez? Jacqueline? Jacqueline? Gonzalez? Not here. All right. Natalie Jackson, are you here?
Yes.
Thank you. Is Jasmine Law here?
Yes.
Ivy Lone, are you here?
Yep.
Nicole?
Yes.
Thank you. Gabriella?
Yes.
Ryan Marks?
Hello.
Good. Sam Mohammed?
Yes.
Thank you. Fan King Chi? Fan? See,
Yes,
yeah. Okay, you're here?
Mhm.
Kwa? Julie?
Here.
Okay. And Catherine Silverster?
Here.
Thank you. Nathan, you're here, right? Is Diana here?
Here.
Thank you. So we're missing one person. Jasmine, is it Jasmine not here? Gonzalez. Jacqueline Gonzalez not here. Okay. All right. All right. I just want to make sure everybody here sees. Well, yeah, after so much work, you finish the reaction, you're able to collect we call dicarboxylic acid final product. We call hydrolysis product. Sometimes it is referred as dicarboxylic acid. Hello? Dicarboxylic acid, okay? Because there are two COOH, and each COOH we call a carboxylic acid. So it is a dicarboxylic acid, okay? And I told you when we run the reaction the first time 5 years ago, the whole 300 students class received less than 0.5 grams at the end, okay? That was heartbroken. All right, recordograms.
There's a lot of glare on the thing and I can't really read it.
I'm sorry, are you able to see my screen with scale?
Yeah, it's just the scale is like there was glare on the reader, so it was hard to read for a second.
Yeah, the
Oh.
light on it.
Okay. Is it better? This is the grams, okay? Hey, ladies and gentlemen, are you writing down the grams?
Yeah.
Okay, I will not go by other number you created, okay? It has to be the number I want. Okay, so today is 23rd. Okay. All right, students, remember melting point experiment?
Yes.
This TA is amazing when he. Okay. So what do we see here? Well, you take a guess. I don't want to tell you. There are two samples only, okay? 64. You know, the whole video was accelerated, like fast forward when he recorded it, okay? Or else it's too time consuming. Like actually he heat up the sample slowly, okay? Okay. Cyclo addition product is on the right. So what is the target again? Temperature?
78 to 79 degrees Celsius.
Okay, let's see. You better write down, okay? I want you to tell me what the melting point is. Yeah, obviously he slowed down a little bit. Okay, one more time. Did you see the sample melt? It was like this, okay? It's probably not very clean. Ah, okay. Did you see did the look being changed a little bit?
Honestly, I had a hard time seeing it.
Mhm.
Was it just like the white kind of crystal turning clear liquid
Yeah,
on the left side? Oh,
yeah. Let's see. Okay, now this is the hydrolyzed sample. That means it has two. Okay, do you see how it collapses in the capillary tube? Do you see
yeah.
how it goes? Now, it's more obvious with the hydrolyzed sample, right? So what was the temperature? Now you guys recorded, okay? Look at this. Is it melting? Yeah, it's melting. Yes, right? Okay. And you record the temperature when it's begin melting and when it finish, completely liquefy. Okay. Are you able to see some big, oh my goodness, I better go back. Now, students, are you able to enjoy the video? Hello? You don't do any work, but are you able to enjoy it?
Yeah.
Yeah. I have one question for the last part we saw.
Mm-hmm.
So was the hydrolysis product range like 200 degrees Celsius to 204, or was it? Is it from like when he started recording that part to the end of it?
Why don't I replay it? Okay. Can I replay it?
Yes, please.
just please.
Okay. replay, okay? It's more clear right now. It's, you know, sometimes it's actually getting quite clear. I mean, it's only a matter of the angle. A lot of times it's angle. But it's in this range when you observe, when you can observe some liquefying and the hydrolyze. Yeah, he's the TA tried to save your time, okay? It was a long waiting period. The hydrolyze actually, hello, I think it started at 199, something near this range, right? Do you agree? You can see the sample actually start liquefying. Are you able to see that?
It's really hard to tell through the video as opposed to like being there. So I'm not sure personally.
Okay, let me do it again. It's not as clear in the cycloaddition. The hydrolyze, okay, look at this. From 194, all right, students. Is it more liquefied now? Relatively speaking, hello? Are you able to see it's
Yes.
liquid? It's more liquid. It already started melting. Look at this. It's completely liquefied here. Okay? Agree?
So we'd put 194 to 202.
From 194, I'm not sure you actually get, you know, I don't know whether you have experience taking the melting point yourself. Did you do it once? Have you ever done once?
We've done it once, but that
Yeah,
was
one
in
time.
Chem 1 lab.
One time? Yeah. Let me tell you, the packing of the powder will actually help you see much better. In other words, you don't want air pockets, okay? If you see air pockets, the heat transfer is bad. And also the melting behavior becomes a little bit confusing. You don't want air pockets, okay? See, so here, I would say it probably start melting here at this temperature, okay? Because it's more and more clear. It began to melt, what, 97 or something, okay? Look at this. Completely collapse, right? Okay, so it was broader range and it's not as high as the literature, okay? Imagine students, we're not able to give you a perfect solid sample, number one. In the summer, when we video this whole demo, try to understand, we're only allowed to stay in the building like for 4 to 6 hours per day, okay? That's, you know, according to our safety regulation. The dean does not want to increase the risk, okay? And so try to finish the work as much as we can. And also oftentimes we have problem with the issue room. We cannot get the materials ready, etc. So even when we prepare this sample for melting point, we're supposed to make, you know, packing 100% perfect, no air pockets. Okay, we want to wait for the salt complete dry before we can take the melting point. We cannot afford that in the summer at all. Okay, it is all because of We only have very limited amount of time in the building. Understand? So I have to tell you, the TA who's able to do this much work within a day is already breaking the record. You may not believe it. It's so true, okay? So I was really, really happy with this TA, okay? No wonder he received the outstanding award and then outstanding thesis, etc. Okay, and look at this, it's completely collapsed, okay? And so I hope you're able to enjoy it, okay? I gave you the, I think we played a couple times already. Are you able to write down what you want? I mean, the ideal data? Even a little bit imperfection, I can understand, okay? But you cannot just give me any random number from the top of your head, okay? Students, any question?
Just a quick question on the worksheet.
Okay.
So for
Okay, Simon, let me open the file
okay.
so I can help you better, okay? All right. Share screen. Okay, now before that, I see a question coming from somewhere. I want to know. I want to know who gave me the question. It's okay. You can tell me later, okay? Now, students, I really want you guys ask question. It really helped me clarify a message, okay? Now look at this. Miss Jean has to develop how many things for the entire course. Okay, and this is the PE master package. Okay, what is the page number on the worksheet now?
The page I'm looking at is page 12.
Okay, 12. All right, students, are you able to fill in the blank here?
That was gonna be part of my question. Is so we're writing the equations in sequence, doing like the cycloaddition equation and then the hydrolysis equation.
Okay.
But when it says indicate the movement of electron pairs, are we just drawing the mechanism for it?
Yeah, actually, I show that all the time to you, right?
Yeah, and then so do we have to do the mechanism for the hydrolysis, or do we just do the mechanism for the cycloaddition?
I asked you for cycloaddition. I will not ask you to do more.
Okay, thank you.
Okay. So there will be, reactant. I want to see your structure, molecule structure, okay? The reason I want to make 2 points, a lot of students give me chemical formula, like C5H12. I mean, I don't want that. I don't want formula. I want structure, okay? Okay?
For part 2, in the cycloaddition.
Wait a minute. I think in the entire experiment, sorry, I think there are 2 questions right here. You want to get me reactant, then product of reaction 1. Then show me how do you do the reaction 2 today. But you show me the movement of electron pair when you do this cycloaddition. Understand? Simon?
I'm sorry, can you repeat the question?
I said I want the entire experiments. The entire experiments involve 2 reactions, right?
Yeah, so we basically draw the reaction that makes the cycloaddition product and the reaction that makes the hydrolysis product.
Yes.
But we only draw like the arrows and stuff for the cycloaddition product.
Exactly.
Yeah, thank you.
Follow exactly what I say here. It is for you to write down the molecular structure, practice mechanism writing a little bit, okay? All right, and then table of content, okay? Enter the numbers, okay? And then you tell me theoretical yield, okay?
I have a question about part 2.
Okay.
For the cycloaddition product, for the grams, I have 2 values and I don't know which one it is. Like
I also have that too from the last time. Yeah.
Yeah.
Can you share screen with me?
I don't have it on my screen. I have it written down in a notebook.
Me as well.
And no one can share screen with me, right?
No, I mean, I could dump the numbers in chat.
Hey, give me a break. Why do you have 2 numbers? Tell me.
It was just the last, from last time, there was, for the Cyclo Edition product, they said 1.252 grams, and then today, at the beginning, said 0.604.
That was the amount we used for reaction 2. Okay, last time we weigh out 1 point something grams when we finish the reaction 1, that it's a Cyclo Edition product, right?
Mm-hmm.
But today we start off reaction 2 was 0.6 something, right?
Okay. So for the Cyclo Edition product, it's going to be the 1.252 grams.
Exactly.
Right? Okay.
Okay. Yeah.
Thank you.
Exactly.
Thanks.
There are 2 numbers, you're right, but one is actually the product we crop, okay? And then today we have, because we didn't really use all of it, we only use a portion of it, so we weigh again, right?
Got it.
Okay, now here, questions. I can tell you, students, question part C is actually a little bit harder, okay? I'll come back to that later, okay? But are you able to handle questions here? Your comments on melting point and purity, okay?
Yes.
Are you able to handle, why one of the product has such a high melting point? Okay, you should know that, okay? Now part C is tricky. Part 2 right here is stoichiometry. And why do we want to add extra? Okay, I want you to distinguish the IR, okay? That's actually up to you, okay? I'm not going to tell you the answer, but part C, it's a little bit tricky, okay? And let me show you a little bit of my insider information, okay? Let's read the question again. The Cyclo Edition product exhibits a different reactivity compared to the hydrolyzed diacid product. If the hydrolysis to the diacid is not complete, then you will have a mixture of the 2, okay? Do you understand the question now? And I want you to find a way, how do you separate the desired diacid from the unhydrolyzed anhydride by acid-base extraction? This is a hard question, okay? I can tell you, I want you to take notes. I can give you a hint, but I'm not able to give you an answer, okay? Are you ready?
Yeah.
Yeah.
Okay, because I'm gonna switch screen, okay? Okay, share screen. Remember this? This is my Cyclo Edition product, right? I'm sorry. And then this is my hydrolysis product, right?
Yeah.
I'm saying if the reaction is not complete, then you will have the reaction mixture, or you can have the powder. These 2 products are mixed together. Am I right? If the reaction is not complete, then not all of the Cyclo Edition product can decompose or hydrolyze like this. Am I right?
Yeah.
Yes.
Okay, so how do we separate them? By acid base extraction technique? This is the question. How? How do you separate them? Tell me by just looking at this two structure, which one is a good proton donor? Which one is a good acid provider? If I call this 2, and if I call this 1, which one is a better acid provider?
Number 2.
Number 2 is, am I right? It has a hydrogen right here, and COOH is capable of releasing hydrogen proton, right? And because this is a weak acid going back and forth, there is a Ka. Have you learned this term? There is a Ka?
Yeah.
Equilibrium constant.
Okay, yes. Acid dissociation constant, okay? And we know this is a better acid compared to that, right? I don't see any proton here. So tell me, which one reacts with strong base and with this hydrogen right here? Do you think it will react with, of course, the strong base will kill it. How about a weak base? If I give you a weak base, such as this, sodium bicarbonate, okay, and has a very low tendency producing OH, and this is a weak base. Are they going to react with each other? Is there a reaction? You don't have to answer me, okay? How about this guy? In the presence of anhydride. In the presence of this. Before hydrolysis. In the presence of this. Tell me, is there any reaction? If I can react with one of them and leaving the other one untouched, then I can separate them. Am I right?
Yeah.
Okay, and think along that line. I already gave you the hint, okay? So what will be a good way to separate them? I think I'm telling you a good hint. Okay, so do you want some reagent? Okay. How about comparing sodium hydroxide and sodium bicarbonate? Have you learned the term strong base or weak base?
Yeah.
Have you learned that before? Okay. So do you want a strong base or weak base here? Or do you want a weak base? You can dissolve one of it and the other one does not dissolve.
We would want a weak base so that it doesn't affect the cycloaddition product.
Definitely, Simon, you're on the right track, okay? You're able to collect my hints so quickly. All right, the rest of you, I don't want to tell you anymore. You should be able to come up with the answer from, just like Simon, okay? Simon did a very good job, okay? And I'm so sure that I have students who are capable of making a very good grade at the end of semester. Students, entire class, I want you to ask me a question before I say goodbye. Are you able to handle this question now? Hello?
Yes.
Yes.
Yeah.
Okay. The due day is today and 5 o'clock. Okay, I'll set up a Dropbox, okay?
Are you gonna post the recordings for last class and this class?
I can post, yeah, I can post for today. From last time, do you guys need them?
I would personally like having the recording from last lecture. I don't know if anybody else would.
From last lecture and from today's lecture too?
Yeah.
Okay, Simon, I really want to help, but the thing is, I will upload the video, but I don't know, sometimes the YouTube, because I'm uploading on YouTube, okay? I'm not sure they will make it a valid video right away. Sometimes it takes a couple hours. Do you understand me?
Yeah.
Okay, I'll upload it right away, okay?
All right, thank you.
All right, students, before I say goodbye, any more question?
I have a question on the IR spectrum. When it says to comment on the key peaks, do you want us just to list the functional group? Or do you want us to include the functional group and intensity? Like, how do you want that to be?
In order to distinguish, you always need to describe what peak you're looking at, okay?
Okay, so you're gonna list the peak number and the functional groups?
That's right.
Okay.
You want to know, yeah, which bond is responsible for the difference, and what is the wave number? Okay, tell me what is the position of the peak and what is the bond associated with that peak. Am I clear?
Yep, got it.
Got it. All right. All right, the rest of the class, are you comfortable now?
I think so, yeah.
Okay, I'll say goodbye. All right.
Alrighty, thank you.
Bye.
Thank you.
Have a good one.
Bye.